So in 1417, we're trying to predict the product that you would get for the reactions of some epoxides with strong nucleophiles, and also we're trying to draw the mechanism for this. So in this next example, in E, we have a funny looking epoxide. So we've got that epoxide ring, and on one side we have an ethyl chain, that's what the ET is standing for. On the other one we have a benzene ring acting as a branch, so that would technically be called a phenyl branch. And then coming out at you on this other side we have a methyl branch. And so just like before, in earlier parts of this problem, the oxygen is really electronegative, so it pulls the electrons in those bonds towards itself and becomes slightly negative. And whatever it's bonded to becomes slightly positive. So those two carbons in the ring. So that is our epoxide. Now, they give us a nucleophile, and the nucleophile is NaSH. And the pattern we've been seeing is that anytime you have a metal, the metal has really low electronegativity, and so the metal itself loses its electrons and gives them away to whatever it's bonded to, and that thing becomes the nucleophile. So the metal goes off, lives its own life, and here the nucleophile is going to be SH with a negative charge. Now there are two places this SH could attack. It could attack the slightly positive carbon on the left here, or the slightly positive carbon on the right. Neither of those are a nucleophile's dream. They're both a little crowded, but this carbon on the right is less crowded. After all, it is a 1, 2, a secondary carbon. This one on the left is a 1, 2, 3 tertiary carbon. And so by that alone you can see that this is more crowded. So the nucleophile definitely is not going to attack there. It's going to attack the less crowded carbon, the secondary carbon, and so it attacks that. And that carbon already has 4 bonds. In order to form this new one, it has to break a bond to make room, and the bond that breaks is the bond that is the weakest already because of this difference in electronegativity. The electrons are already spending most of their time around the oxygen. All it needs is a little push, and that bond pops open, the electrons go toward the oxygen full time. And so here we are going to, now another point actually, maybe I should be a little more precise in the way I draw these arrows, is because here the bulky areas are all on this carbon are pointing down. That methyl branch is pointing down, and so this SH is going to attack from the top. And so when we draw the product, we could have that SH at the top, and this way, if we draw it that way, we don't have to worry about changing any of the stereochemistry elsewhere. So we have the ethyl group going down toward you, the phenyl ring, the benzene ring acting as a branch, going down and away from you, and then just straight up you would have the oxygen. That oxygen has a full negative charge, and so just to stabilize that molecule, we would want to add water. So you shake it up with some water. Water is very polar, oxygen slightly negative, the 2 hydrogens slightly positive, and so this oxygen will attack the hydrogens, kicks off the electrons, which go toward the electronegative oxygen, and you have your stable product. All the other chains stay the same. And then just going up, you'd have an O with an H and no charge. And so that beautiful molecule here is what you'd get when you mix this epoxide with that nucleophile. Okay, so let's take that and actually take this and make it a little less bulky. And so here we have our last one in this problem. We've got our crazy looking epoxide, and actually it looks like it's the same one as last time. So you've got this ethyl group and the phenyl ring, in other words, the benzene ring acting as a branch. And we know oxygen's very electronegative, pulls electrons to itself, becomes slightly negative. The two things it's bonded to, that it's stealing electrons from, becomes slightly positive. And the nucleophile we have here is LAH. Now remember, LAH is not three atoms. In fact, there are no atoms with just a symbol of capital L or capital A, all by themselves. And so that's really an acronym standing for lithium aluminum hydride, LiAlH4. And what you would want to be able to draw for that is an aluminum with 4 hydrogens. And each of those hydrogens are slightly negative. You don't usually think of hydrogen as being electronegative like that, but it's bonded to a metal, and so electrons flee metals. Metals have such low electronegativity, they just can't compete with any other element. So effectively, this is a hydrogen nucleophile. So you can take one of the hydrogens, let's take this hydrogen here, that's going to pick up its electrons and attack the less hindered carbon. And again, let me draw this from the right side. Of these two carbons, like we saw last time, it's the same molecule. This one's tertiary, this one's secondary, and so the one on the right is less crowded. And so this is going to pick up its electrons and attack that one. That pops this ring open, like we saw last time, and you'd get the rest of these branches staying the same. So the ethyl group, the phenyl branch, benzene acting as a branch, the methyl branch, and then coming off of this we have that hydrogen going up, and on the other side the O with the negative charge. So just to help stabilize that, we can shake it up with some water. We know that oxygen's very electronegative, becomes slightly negative, whatever it's bonded to becomes slightly positive, and that negative oxygen plucks a hydrogen off of there. The electrons in the bond go toward the most electronegative place nearby, which is the oxygen, and so you're left with all these other branches staying the same, just with the O here having a hydrogen on it and no charge. And that beautiful masterpiece right there of a molecule is what you get when you do this reaction.